My name is Dan Pollock. I'm the CTO at Data Storage Science. This is a talk on a project I built about low latency and scalable key value store from modern off-the-shelf components. That's a long title and a lot of words. It's a much simpler thing than that makes it sound like. So I'm going to go over the project and why I think the project is worth doing. Take you through the sort of mechanics of how it works and how I implemented it, look at the evaluation of the project, and then maybe discuss some of the possible follow-on potential for some of the work that is being done in the industry and in some other places around the community. So what's the project itself? So it's low latency key value store, right? People like low latency. Key value store is a interesting way to store data. A lot of what you see when you talk about some of these components, in particular NVMeoF, is people looking at throughput. In this case, I thought operations-based workloads were more interesting as opposed to throughput workloads. Both are valid kind of things to do, but in this case, I thought it'd be interesting to investigate small key value data storage as opposed to just sort of raw throughput stuff. There's only two components for the project, and based on what you think components are, one might be a little bit more complicated than that, but it's basically software, which is MinIO, and hardware, which is an NVMeoF TCP storage array from Lightbits, although while Lightbits was generous enough to provide the array for my lab and for the purposes of investigating kind of use cases, the NVMeoF TCP storage capabilities are open source and implemented in a number of different places, including the Linux kernel. So if you want to build your own, you can certainly do that, and I'll talk about that some more later as well. What's MinIO? Just a quick review. I'm sure most people have heard of it, but it's a simple object storage front end to any sort of file system storage that you have on your back end. So it's designed to just convert from one generic set of protocols that may be on the back end, either file system access or any other sort of like NFS access, to object access for people who would rather access their storage through an object mechanism as opposed to something more complicated and more traditional like a file system interface. So be that as it may, it's a very simple thing. It's a single command line for the server, and there are very few options to that command line. So you can create very scalable, very performant clusters, or you can do a single storage server all on its own with the same command line, and there are very few differences in how you implement it. So that's one of the nice things about this, is incredibly simple and straightforward. There are an enormous number of features as well that I won't get into here. Maybe in the follow-on I'll do that, but in the meantime, it's very performant. In addition to being scalable, it supports many gigabytes a second of throughput, depending on what you put as the back-end storage that supports it. And it also supports the same sorts of latency that the back-end storage has. So if you have very high capacity, very low throughput storage, you get that. If you have very high performance, very high throughput storage, you get that. Also, one of the nice things about MinIO is it's incredibly manageable. In addition to just having the simple one-line server, when the server comes up, you can control it through the server command line, but you can also manage it through an API. So you can provide programmatic control for external management software very simply. And it's open source, so if you don't have what you need in it, you can either request it or contribute changes that you need directly yourself, and the community will add them if they're theoretically of value. The other component of the project is the NVMeoF TCP array. Like I said, I got mine from Lightbits Labs, but you can create them out of the open source components that exist In particular, in the Linux source code includes both the target and initiator components there, so you can create end-to-end solutions basically for free as long as you have the hardware to run them on. There's no additional software cost. The LightBits Labs implementation is slightly more interesting than that. Not to get into it too much. If somebody has specifics, we can go over it in the Q&A. But in any case, it's basically an open source NVMeoF TCP target, and it's very high performance with very low latency and very high throughput. The default config for the LightBits appliance is a 100 gigabit Ethernet connection to the storage clients, and it runs at full speed. So you will get over 10 gigabytes of throughput if you have the client load to drive that. Once again, I didn't look at the throughput of it, but it's nice to know that the throughput is there. And like I said, the average latency just for the storage array itself is very low. In this case, right around 120 microseconds is what the LightBits guys have published for their specific implementation. One of the other interesting things about the NVMeoF TCP array is that it uses common infrastructure. So I have 100 gigabit backend, so I don't need any new hardware. I simply plug my array into the 100 gigabit backbone that I have. And at that point, I have 100 gigabit NVMeoF storage target available to anything on my TCP network. So even though I have a very high performance array, I didn't have to perform any specific infrastructure upgrades to get there. So it's a standard server system. If you don't want to get one with the specific hardware implementations that LightBits has, you can do it with just straight up standard server with NVMe storage inside of it, and it's standard Ethernet networking. So because it's all included in the Linux kernel, any Ethernet networking that you have that runs TCP over the top of it is just going to work with your NVMeoF TCP array, assuming you have the right kernel modules built, and the stuff that's included has been part of the GA kernel since the 5.x release, and there's some pre-GA stuff that's in the earlier releases. But so me in specific, I'm using 5.x kernel here. There's it's a Debian for the most part other than that, but it runs just fine without any changes at all other than enabling those capabilities within the Linux kernel, which don't ship today with the default configured on, but there's nothing complicated about enabling them. So those are the two components. MinIO is the software, NVMeoF TCP array is the hardware. And so the question is, what is this good for, right? Why is this even worth doing? And I think it's worth doing because it's both an interesting experiment, but it's also kind of an interesting use case in that people will be using key value stores for a long time to come and implementing them in simpler, easier ways, even if you may have to make some trade-offs there, are, I think, a useful thing to do. So while I was mulling over kind of what use cases would be useful for NVMeoF and looking at how those implementations are probably going to go, I thought to myself, gee, everybody's talking about throughput. Let's look at, high operate, small IO, and see if there's something of interest there. And I think there is. So I went through this whole thing. And so one of the other things people point out is that, software can get complicated. So keeping it simple with something like MinIO is a good way to go for even production implementations, even if, like I'm doing experiments here and then kind of moving them out into places where people can use them for our customers. The idea here is that it's very, very simple. So there's not a lot of things to worry about when you're talking about the moving parts or the trade-offs and complications or the software implementations or how much infrastructure you have to build, because the answer is almost none to all of those questions. One of the other things that folks brought up when I was talking about this is that, key value and object aren't the same thing. And that's mostly true, although in my head and, based on the definitions, key value is a specific type of object storage. When you look at some of the definitions of what a key value store is, it's basically fixed length keys and fixed size or non-split values, right? So object stores can have variable length keys and multi-part components of the object being stored. And that, to me, is sort of the only real difference, and it looks like a hair-splitting one. So I think, even though MinIO is officially an object store, it'll work just fine as a key value store. And it turns out that's totally true. If you put in fixed length keys and single small values, you get exactly what you'd expect, which is key values. One of the other things about key value systems that are common is that they tend to be implemented in DRAM because the small IO behaviors are conducive to very low latencies, and implementing them in DRAM lowers the hardware latencies and access latencies effectively as well. And because the NVMe storage systems are also very low latency and very high throughput and very high performance, I thought to myself, gee, what's the trade-off there? And so while DRAM is definitely going to be faster for all the use cases, or for most of the use cases, I'm sure you can find ones where it's not as fast. The NVMe storage is going to be much, much cheaper for sure, somewhere between 10 and 100x, depending on what you're buying, DRAM versus NVMe storage, and also much higher capacity. Getting a terabyte of DRAM is fairly expensive and requires a lot of DIMM slots or very dense DIMMs in whatever servers you're getting. So those aren't difficult to find these days, but they're certainly not cheap. And they're certainly not as common as something like a 1 terabyte NVMe storage device, which are basically everywhere. And NVMe storage devices are now up to 16 and 32 terabytes in capacity. So compared to DIMMs and DRAM footprints, NVMe storage is much lower cost and much higher capacity. And those sorts of things always seem really interesting to me when you're talking about consolidation of resources, because that tends to be where people go to reduce cost and improve efficiencies. So the disaggregating the resources, right? You could certainly build those devices, and you can even build a MinIO cluster with storage in each individual server. The problem is that once you've committed that, you can't use it for anything else. So if you have the need for something that isn't a MinIO cluster, you will have to figure out how to expose any storage that you've stuck inside a dedicated server in some way. And so that you'll either wind up implementing NVMeoF target on your own on those specific arrays, or you'll wind up aggregating the storage into one place and then accessing it as a disaggregated resource across multiple consumers, be they a MinIO cluster here or a database there, or even something like maybe VMware in the future, depending on how enterprise implementations go. So what you'll find is that even though people can dedicate resources to the individual projects that they want to service, in the end, what you find is that, especially in the enterprise space, you get disaggregation, you get consolidation, and you get resource sharing, because that tends to be lowest cost and most efficient. And then sort of the other thing about why I think this is one of the other things about why I think this is worth doing is that the TCP networking is everywhere. It's universal, it's ubiquitous, and rebuilding and deploying or building new and deploying uncommon infrastructure is not incredibly popular. There have been a number of technologies, and there continue to be a number of technologies that are either higher performance or more efficient or more specialized or dedicated to certain tasks. But the problem there is that people are constantly making trade-offs where if I have a network that's dedicated to this specific transport, then I can only do what those things allow there. Whereas with TCP, I might have to, in this case with NVMeoF, TCP, trade off some latency at the minimum and some maybe throughput at the maximum. It's definitely a nice thing that I don't have to do any additional work to get it deployed. So while I'm not getting the absolute greatest benefit, I'm getting a much simpler, more efficient implementation. So that's sort of the trade-off that you want to make. And then one of the other reasons I think this is actually worth doing is because, or a number of other reasons I actually think this is worth doing, but there's actual need for this, right? The idea that you want to access NVMe and you want to access it over the network, and you want to not have to do an entire rip and replace in your environment to make that a thing that you can do pretty effectively. And in this case, all you have to do is acquire the NVMe target, right? The NVMeoF array target, whatever that flavor is that you prefer, at whatever cost you can handle, and suddenly you have that available to any TCP client consumer on your network. And your mileage varies based on how your network is built and how robust it is and how performant it is. But at the end of the day, you almost had to add nothing beyond storage that you were going to have to add anyway to implement whatever project you were going to add. So it fulfills actual need. And one of the other nice things about how simple it is that it's really rapid to evaluate. It takes a very short time to implement an entire MinIO cluster. It takes a very little effort to get the NVMe array set up and exposed to the clients. It takes the clients very little effort to start accessing the NVMe storage. And because of that, it becomes very simple and very quick to be able to say, let's try that with the NVMeoF array, or let's try that with NVMe storage and see, does it meet our needs? Does it make the right trade-offs? And is it the right answer to the data storage requirement that we have? And in this case, I used key value as the data storage requirement, but it doesn't need to be that specific, right? It can be pretty much anything that requires access to high performance storage, which is pretty much everything that's a tier 1 application, and being able to deploy the NVMeoF quickly to know whether or not it's a valid use for the project that you've got is a really useful thing. So you don't have to kind of wait to see if the result is what you want it to know, what you want it to be. This way you can just turn it on, make access happen, and run your project or your application and see if it works. And then you know the answer. It's either good or it's bad or it needs tweaking. But at least you don't have a tremendous amount of cycle time through getting it set up and getting it tuned and getting it evaluated, and then kind of going through that over and over and over again. So what did I do? I took the NVMeoF TCP array and set it up to provide storage to hosts, so to multiple host systems that form the MinIO cluster. The MinIO cluster is running on those host systems and exposes those NVMe storage devices as object storage devices to the clients through the native object APIs. One of the other interesting things about MinIO is that it has a number of access options, including industry standard S3, among other things, for its object accesses. You can do you can make the choices that you need to make, and in the case of something like S3, you can even plug it directly into something that already talks S3, and it'll be compatible in that environment without having to create any additional middleware to make that work. So then the last part of the implementation that I did was the client side, which is the clients are just MinIO clients that make key value requests. I use 2 clients for my eval. One is just a native API client implementation that I wrote in Python just to get a feel for how things would work, and the other is an industry standard YCSB performance evaluation tool for the purposes of just sort of normalizing the results for what people are used to seeing as opposed to my own eval code. So this is what it looks like. This is exactly what it looks like really for servers to file systems on each server, that they all come from the NVMeoF array. So NVMe traffic is sort of north and southbound. MinIO cluster traffic is east and westbound. That all uses the 100 gig switch. The client side network is a 1 gig network, just because I wanted to keep those separate to avoid not contention on the 100 gig, but just to avoid having all the network traffic sort of artificially go through the artificially high-speed storage network, as opposed to what you would get from a typical front-end network. And these servers, like I said, are kind of old, so they have 100 gig, or rather 1 gig front ends, even though they have 100 gig back ends. And eventually we'll upgrade them to 10 gig, and I'll probably rerun this stuff. But basically what you get is sort of an equivalent latency reduction on the front-end network from increasing the front-end network speed. So once again, this is just sort of a demonstration of how simple it is, right? You do NVMe storage discovery for the NVMeoF stuff. It's basically a one-line inquiry command from the client. So you run it on every client. Then you get access to the storage devices that are provisioned to each client, and you format them into file systems in this case. And then you run this one MinIO command at the bottom, and that is the exact MinIO command that I used, which basically says, run MinIO as a server, use the following hosts as cluster members, and use the following file systems on those hosts as storage devices. And the ranges there just basically are so you can avoid enumerating each host and each file system specifically. But it does not get any simpler than that. And when you're done running this command on all the hosts that are going to be part of the MinIO cluster, you have a fully formed MinIO cluster. So once again, like I said, this is how I did the eval. I used YCSB for workload evaluation, and I wrote some native Python tools with the MinIO Python SDK so that I could get those sort of eval numbers as well, just to get a feel for the implementation itself without dealing with the sort of YCSB complexities there, because YCSB is a very capable tool with a broad ability to apply benchmarking to numerous databases. And it was a little bit more of a learning curve than I wanted to go through to become a YCSB expert, just to evaluate my NVMeoF TCP key value store in the lab. So I ran mostly stock YCSB workloads with that tool for comparison purposes, and I have some results from my Python API implementations that are just basically behave as clients for both of those things. One more thing about this, the Ethernet front-end network has about half a millisecond of latency built into it because it's a 1 gigabit Ethernet network. So that's gonna, and because the performance is measured by the clients as opposed to just through the back end, the lowest possible latency for the round trip would be half millisecond or 500 microseconds. So now that it's set up and it's running and there's test evals, so what did I get from the latent for the native API creation of the key values? And so I chose a 16-byte key and a 200-byte value, which seems to be reasonably standard kind of implementation for key value stores, or at least for the evaluations of key value stores, as far as I could tell from the literature that I'd read about key value store performance evaluation. So here I do 1 million key value stores just to populate the key value database. Like I said, 16-byte keys, 200-byte values. Mostly they perform pretty well, and between 1 and 3 milliseconds, you get about 98% of the keys stored. A little bit slower for a couple percent of the workload, but all in all, not a bad write workload speed for this size of data and this infrastructure. So now this is the native API doing reads or gets, and this is fetching random keys from the key space and it's performing 4 million gets for the entire, so it's 4 million random gets in the 1 million key value space, right? And so the idea here is that most of the gets perform or come in at under 3 milliseconds for retrieval times, and that's right around 2/3 of them, and then right around 1/3 of them are somewhat much longer, and then there are some in between ones, and so there's some stuff going on here that I did not have time to fully investigate, but I'll have to kind of work my way through that as I move this implementation from the lab to our customers. I suspect that there's some either caching or startup effects, or maybe even some network effects that I'm seeing just from something I'm overloading, but I'll get to the bottom of that in the future. So then just for my own sort of interest, I went ahead and I said, what happens when I delete all the keys and values from the data store? Because that tends to be a workload that people want to avoid, because deletion tends to impact workload that's going on that's much more important than just making space and housekeeping, right? So it turns out that deletions are very high performance as well, which is nice in that 100% of them come in under 3 milliseconds no matter what you do, and it's about half below 2 milliseconds and about half between 2 and 3 milliseconds. So you get this very high performance ability to delete data as well, which is one of those things that people generally don't need to do, although when people do need to delete data, they find that it tends to impact the performance of the running system adversely. So knowing that you can have very efficient deletes in the system like this while it's doing all the other work is kind of handy and interesting to know. Okay, so now here are the YCSB tests. So these are much more, I guess, standard in that this is what people do for evaluations of databases and key value stores and all kinds of other things related to this sort of thing as well. And so this is the load phase insert latency for 100,000 100-byte keys with 100-byte values, because that seems to be what the YCSB standard is. And so, or rather 10-byte keys and 100-byte values, I'm sorry. And this is the creation of the database latency, basically, and it's actually pretty performant. There are some high latency tail requests as well, but for the most part, the average is pretty low at less than 2 milliseconds, and the minimum is right around 1 millisecond, which is sort of reasonable for performance for creating 100,000 objects in the database with the 10-byte key and the 100-byte value. So then there's this kind of choice of workloads that you have with YCSB. And in this case, I use the 90-10 workload. I think in general, that's a reasonable assumption that most key value stores will be not just read mostly, but almost read entirely. And so I have, in this case, that 90 indicates the reads, and the 10% of the workloads are new inserts as opposed to updates. There are no updates in this workload, which is another thing you don't really get in key value stores very often. Rarely are keys updated. From my experience and from what I can see in the literature, keys are rarely updated. They're primarily just inserted as new if you want to insert new data, and old keys are either deleted or what have you. But in general, this is the YCSB workload that does just reads and inserts. And it's the same 10-byte keys, 100-byte values. And this is like I said, this is the insert part of the workload, and the numbers are still pretty good here. The average is much higher, but the minimum is not terribly high. And then once again, the tail latencies are big, but they're not killer. There aren't a lot of operations at those very high numbers, right? So the 99.99 percentile is in 100,000 inserts is, I forget, something like 90 total ops in the 100,000 workload. So that's reasonable, although once again, it's sort of related to what your, or at least I think it's reasonable anyway, and it's related to what your workload absolutely needs to be. So if these tail latencies are too high, then obviously tuning is required, but for these purposes, I think, for me evaluating this, this looks fine. And so here's the read latency, which is the same million operations of workload, 90% of those are reads. So this is the performance that and this is the latency that you see for that workload. Once again, the average is pretty decent and the minimum is very low. The maximums are higher. So like I said, I think there's some resource constraint that's driving those maximums higher than they would normally be. And I do have to go figure out what that ultimately is. And one of the ways that I validated that there is some contention somewhere in here that I have to find is that I did a test with 100% reads and no inserts or updates at all. And this is what you get. And it turns out that the maximum and the 99.99 percentiles go up even while the average and the minimums go down, right? So the average latencies drop, the minimum latency drops, or basically stays the same, and the maximums go up. So that tells me that there's some contention somewhere in the system that I built, which is my fault, but I'm pretty sure I can track that down and address it and bring the tail latencies down to something much more palatable, because when you look at them here, as far as reads go, they're okay, and as far as inserts go, they're okay. So I think I can find this and fix it, and that's sort of a TBD, but at least it's something that I know is part of the system and means that I have to at least manage that from a implementation perspective when I get to that point. So here's sort of the conclusions of how good it is. I think, like I said, the round trip network latency is 0.5 millisecond. So that's the low bound for any request in this system. When looking at the literature, it looks like 1 millisecond is a key target for read response time, and I'm not quite reaching that. API reads are only about 40% within 2 milliseconds. YCSB average is slightly over 2 milliseconds for the read workload components of those workloads that I chose. So this is okay, but not great. So I would obviously either look to do performance improvements or performance tuning, or to make trade-offs, knowing that 2 milliseconds is a much more achievable goal than 1 for this type of system. Although no tuning at all has been done, it's basically just been install MinIO, install the storage array, configure it, and test it. So like I said, reads are between 1 and 3 milliseconds for the most part, with 2 being right around the average, and that's okay. It's not perfect, and it would be better if it was better. So is it low latency as far as my claim goes? I'm going to say sort of, and that's, I think, okay. And then as far as scalability goes, does it scale? And the answer is it sure does. You can build very large MinIO clusters. You can scale capacity up in the NVMe array to many, many terabytes, and you can combine arrays into multiple petabyte implementations, and each individual array is capable of full bandwidth on a 100 gigabit link. So 10 gigabytes per second per array implementation seems pretty good to me. So that's pretty scalable. And then as far as kind of data protection schemes on the back end, MinIO does all of its own erasure coding for the data across systems. It's not configurable, but it is tunable based on how you implement the hardware itself. So there's a little bit of configuration complexity there, but only if you're interested in exotic data protections. If you're okay with the erasure code implementation that MinIO provides, or even just the backend array data protection doubling up on what MinIO provides, then data protection itself is more than okay. And getting the benefit of the sort of disaggregated resource so that you can apply it to any workload, including this one or any other that you come up with, is pretty powerful. So then just kind of a couple of notes about what's coming next in both NVMe and in MinIO, or NVMeoF, TCP, and MinIO. So it is my belief that the TCP implementation of NVMe over fabrics will be the most common one for NVMe block I/O over Ethernet. It just makes the most sense. You don't have to implement anything new. Everybody already has pretty much everything that they need, except for maybe the NVMeoF TCP target system. Those are easy to build yourself. They're easy to acquire from several folks. I got mine from the guys at Lightbits. It's pretty straightforward. There's nothing complex at all. So based on that versus some of the other more exotic Ethernet implementations that are tied directly to the hardware, I think you'll see most people opting for the TCP implementation, especially as it matures. And that's one of the things that's happening, right? Software enhancements are being added to the NVMe standard, and they're all included in the NVMeoF capabilities just because that's how NVMe works. Anything that exists in the NVMe standard is accessible through the NVMeoF standard through just through the network. So protocol-wise, you'll get all the enhancements as time goes on in the fabric stack with TCP, and that's just good for everybody. And then one of the other interesting things in specific to this use case is that NVMe will implement a key value command set per namespace, and that means that you'll be able to not just address the drives in a sort of more basic block I/O fashion, but you'll be able to access them as if they were key value endpoints on their own, and that might be useful in this particular use case and some others to lower latency even further by removing MinIO from the equation altogether. And while there are certainly some trade-offs that you have to make there, because now you don't have necessarily the clustering capabilities, which may or may not give you workload distribution and durability and and availability and some of the other things that you may want, but you'll be able to get at least the key value capability from the NVMe devices natively. And once you have that, you can maybe implement an even thinner piece of software that simply does workload distribution and maintains availability in the cases where you may just want to have multiple copies or even erasure-coded copies of the keys so that you can provide that same sort of capability, but without the MinIO software, maybe even less software, which would be pretty nifty. And then not to get rid of MinIO, because it's got a ton of all useful, interesting things as well. So if you needed replication, for instance, MinIO can provide that between MinIO clusters, and it also provides some versioning, and it provides storage protection classes. So if you want to do different things instead of their basic erasure coding, you can do that. It provides lifecycle management between sort of defined tiers of storage. It provides caching for different types of storage devices in the same MinIO implementation. So if you have Optane, very high performance, and then you have some flash, and then maybe you have something else, even disk if you want, because MinIO allows all those things to happen. You can move data through a life cycle based on its performance or its access patterns or what have you. It also supports things like immutable data. So if you want to have something like a write once, read many, worm capabilities, MinIO implements that as well. And then you can also do things like SQL queries on the data itself if it's formatted properly, and those are all very powerful MinIO API capabilities. And so you could theoretically not just implement a key value store, but then you could implement SQL queries on those key values if you wanted to for some reason. And you can implement much larger data sets and do analytics or some other sort of high-level query capabilities on them. And so that's another thing that you get with MinIO. And you get all that sort of today, and there's many, many more features that I'm not going to get into here, but just there are tons of powerful capabilities within MinIO that allow you to get a ton of useful things done in addition to just my key value experiment. So at this point, I assume maybe there are questions. And I guess because this is a virtual presentation, I'll put up the QA slide, and then I'll put up the thanks for listening, and I hope you found something useful or interesting, or at least enjoyed my talk. And when you get a second, please rate the session and let me know what you thought. I guess at this point, the presentation is complete, and now it's time for the Q&A. Thanks.